Welcome back. In today's lecture, I am going to talk about the Banach space. Okay, and if you see the Banach space, this is one of the very vast topic. But from engineering point of view, I have prepared this lecture. Okay, so just I am going to give you the brief introduction about the Banach space. Okay, and whenever you are solving any optimization problem, okay, it is possible to show that inherently we are assuming that we are in Banach space. Okay, sometimes some exception is there, but most of time our assumption is whatever space where we are optimizing something that satisfy the Banach space. So in today's lecture we are trying to understand that why that kind of space is required whenever we are trying to solve any optimization problem. Optimization problem is everywhere. Okay, all even if data driven prospect, whenever some data driven prospect involved, whenever we are talking about machine learning, whenever we are talking about the optimal control, even if some very specific optimal control for linear system, that LQR some or any other thing, whenever optimization comes into picture, at that time we have to solve optimization problem in some space. Okay, and at that time it is possible to show that a space is nothing but a Banach space. Okay, so before going to Banach space, I will just going to recall the previous lecture. So what we have seen in previous lecture, that if I have inner product space, okay, so with every inner product there exists a norm. Okay, so if I define some inner product and if I just take the square root of that, then norm comes into picture. Okay, so this is one of the way to define the norm. Another way, independently we are defining that is not basically driven from the inner product. Okay, so we have to just making sure that three property. Okay, so here I have written again three property. So this is called positivity. Okay, so whenever I have some vector, okay, now whenever I am talking about vectors, then that might be a column vector, might be a, again same like element, might be in form of matrices or might be in form of functions or combination of that. Okay, so we have to make sure that that is always positive. Okay, so this is called positivity. And zero, whenever we are at zero element, so zero element is defined in different way for different spaces. Okay, now second property is talking about the homogeneity, so this property should satisfy. And third property is called triangular inequality. Okay, so these three property, if some vector will satisfy, okay, then I will tell that I can able to define the norm. Okay, so this is not actually driven from the inner product, this is driven independently. Okay, so some norm is satisfying the property of inner product, some norm do not satisfy the property of inner product. Okay, after that, after defining the inner product, what we are going to do, whatever vector I am going to collect, that I am going to collect from the vector space. Okay, so it might possible I have some kind of vector which will not satisfy the property of vector space, still that is forming some kind of norm. But here in this particular lecture, whatever vector I am going to consider in order to evaluate the norm, that is coming from the vector space. Vector space means I have two binary operation. Okay, one is a scalar multiplication and vector addition should satisfy, and all axioms, all 10 axioms should satisfy. Then only I can define some whatever vector in a space that I am going to give name as a vector space. We have already discussed a lot about that. Okay, now what we are going to do, we are going to add some more thing inside the vector space, that is notion of norm. And why basically we are going to add this, we are going to see in today's lecture. Okay, so now whenever I am talking about norm linear space, So basically I have vector space and I have some way to define the distance. Okay, that is the main distance or length, whatever you tell. Okay, so now if I know the distance and length, then I can able to do lot of things. I can able to define the continuity, I can able to define the limit, I can able to define some topological concept. Okay, I can able to define the nearness or proximity. Okay, and due to that reason, this space, non-linear space, is very important. Okay, what is lacuna of vector space? Inside vector space, I don't have any notion to define nearness. Okay, I don't able to mention the length of some vector. Okay, so length is basically missing. Okay, so what basically we are doing, we are adding the notion of length inside the vector space. That is the motivation of non-linear space. Anyone has confusion? So I hope that things become clear now. I have three axioms. Okay, if three axioms is satisfied by some vector, then that is called the norm, and norm is nothing but the notion of distance. Okay, and if you see carefully, then notion of distance is just coming from the generalization of the notion in one dimensional space. Okay, so in one dimensional space, suppose if I have some quantity like 1, so how basically we are defining distance? We are taking the absolute value of this and telling that this is distance from here to here. Suppose some quantity is minus here, then again we are taking absolute value and taking the distance from here to here, and distance is always positive. Okay, so from here, and if we are here, then distance is 0. Okay, and we know from triangular inequality, suppose that if you can take 3 point x y z, and then this kind of relation will satisfy. Okay, so same kind of things I have generalized in higher dimensional space. Okay, because in one dimensional space I can calculate the absolute value, but in higher dimensional space I have to give certain way to extend this notion of absolute value. So norm basically giving that way. Okay, so now I have non-linear space and I know how to define the length. Okay, so here I have written norm and distance now. So from length, now I am going to talk about the distance. Okay, what is meaning of length? What is difference between length or distance? Suppose I have some kind of vector v. Okay, and if I am going to add this kind of notion, then this is called length. Okay, it means that I am going to calculate distance from the zero vectors. Okay, zero vector from that space. Suppose that this space is x, so I have taken zero vector from this space, and in this way I have defined the length. Okay, whenever we are talking about distance, so in this vector space x, now I have to select two elements, v and w. Okay, so I have selected two elements from this vector space, and now what I am going to do, I am going to see the distance between these 2 points. Okay, so distance between these 2 points can be defined like this. Okay, and this is just generalization of distance in Euclidean space. If you remember in trigonometry, suppose I have this point and this point, and this point I have represented x1, x2, x3, and this is y1, y2, y3. Okay, so distance we are defining like x1 minus y1 square plus x2 minus y2 square and x3 minus y3 square. Like that we are basically here x2 minus y2, x3 minus y3 square, and a square root of that. In this way we are defining. Okay, so what basically we are doing, we are taking the standard dot product. Okay, standard dot product of these two vector we are taking, and after that usual notion of distance comes into picture whenever we are in Euclidean space. Okay, now here we are going to generalize, we are not going to restrict on Euclidean space only. So Euclidean space means I have real numbers. Okay, and after that I have some way to define the distance. Okay, most of time we are defining distance using dot product only. Okay, so same thing we have basically generalized here. Okay, and now if you see this distance, then again that will satisfy this property, symmetry property, because you can see that if we are going to define the norm like this, and in previous class we have already seen, suppose V and W, suppose whatever the vector space X I have considered, so suppose that element of this space is in form of column vector, for just for example I have taken, and suppose everything is real number, so real number x1, x2 and xn all are real number, and that is in form of column vector. So in previous class what we have seen, that I can define the norm, and LP norm I have defined, and LP norm, in order to define LP norm I have again take the help of absolute value. And how basically we are doing that, we are telling that xi square, and after that I equal to 1 LP, P we are telling, so P here xip, and 1 to n, suppose n number of vector I have, and power 1 by P, like this. Okay, and where P I am going to take from 0 to infinity, anything, infinity is also included. Okay, in this way we have define the norm. Okay, now you can take any norm, so each norm is basically going to give the notion of distance. Okay, so now there is not only one way to denote the distance, I have infinite many way to denote the distance. Same like, suppose that I have measuring unit like millimeter, centimeter, decimeter, and infinite dimensional space all are related. Similarly, if you see the norm, so norm in finite dimensional space is also related. So either you can calculate L1 norm, L2 norm, LP norm, whatever norm, all are related. Okay, and distance also going to satisfy the all property. So 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 distance is going to satisfy the property, like something happens. Okay, just wait for 1 minute. So okay, so now distance is also going to satisfy the all property, and here you can see that norm is going to satisfy the symmetry property, positivity, triangular inequality. So all three property is satisfied by distance also. Okay, it is not very difficult to check. Okay, so just distance between vector measure how close to each other. So similarly here if you see this, then we are talking about that any two vectors now, vector may be in form of column, maybe in form of functions, matrices, we are able to talk the closeness of two vectors. Okay, and with help of the norm. Okay, so now norm is very important thing, because I know that how two points are close. Okay, so suppose that if I have this point and I will take third point, so I know that how these 3 points are separated, what is distance from here, what is distance from here, what is distance from here to here. Okay, but suppose now if I have functions. Okay, so how to define the closeness of function? Suppose in a space I have three different functions. Okay, so how to know that this function is close to this function, this function is not close to this function? So for that I need the notion of norm. Okay, and due to that reason norm is very important, because whenever we are going for generalization, so classical way or using dot product I cannot able to do much. Okay, and due to that reason generalization is required. Okay, and if you solve optimization problem, in optimization problem suppose that several time I have to find the optimal trajectory, so I have to find some kind of optimal function, so I have to talk about the closeness of function also. Okay, and due to that reason this notion is very important. Okay, so due to that reason norm, if you are dealing with any subject, you might have seen that people are defining the notion of norm. Okay, another important thing that we are going to discuss, that what is relation between norm and topology. Okay, so far we have seen that norm and distance, with help of norm I can define the distance, and distance is responsible for closeness. Okay, now if my space, if I have column vector, functions, even if polymers, every time polynomials, I can able to define the closeness, okay, using the help of the norm. And different norm can introduce the different way to denote the distance, okay. And these kind of distance is very much important in practical application also, okay. For example, suppose you have to move from your hostel to BHU gate. So this is BHU gate, and this is your hostel. So one way is that you can move from here to here, okay. This is the shortest distance. But most of time, sometime it might possible this road is not available. We have road like this also, okay. Now suppose one taxi is you are going to take, so they are going to calculate distance like this. They first move from here and then they will move from here to here, okay. It might possible road is circular, okay. At that time I again need another way to capture this kind of distance, okay. And it is possible to show that whenever some geometry will change, then different notion of distance basically comes into picture, okay. And due to that reason I need more than one way to define the distance, okay. Now let us talk something about the topology. I am not going to much detail about the topology, just I am going to give you a hint. And here what I have written, the distance between function in a norm function space, okay. Norm function space means now I have vector space, and element of that vector space is nothing but function. That is meaning of norm function space. And now I am going to define the norm which will satisfy all three property of the symmetry, property of the positivity, property of the homogeneity and triangular inequality, okay. So all three property will satisfy, okay. Now norms serve to define the topology of underlying vector space, which determine the notion of open set, closed set, and convergence. Several places you might have seen that people are using this kind of terminology: open set, closed set, convergence, and etc. Okay, convergence is important because we are going to talk about limit in higher dimensional space. So we have already seen what is meaning of limit in one dimensional space, okay. So some from school time we are just dealing with one dimensional thing, and at that time we have seen that how to define the limit, okay. Now since we are in generalized space, so we know that how to define the limit, okay. Another restriction is that now in a space I have element like not only column vector, might be functions, might be matrices. So we have to revisit the notion of the convergence or notion of the limit, okay. So basically if you see the topology, so a topological space is roughly speaking a geometrical space in which closeness is defined but cannot necessarily be measured by the numeric distance, okay. It means that in whenever we are in topological space, at that time norm linear space, you can see that using some kind of number I can talk about the distance, okay. So suppose I have two vectors v and w, and if you take this operator, okay, and if these are column vector, then you are going to get some number. If you v and w is function, then again that is you are going to get some kind of number. So whatever distance, that is nothing but numeric, okay. But whenever we are talking about topology, so topology basically we can able to define the distance but number that doesn't come into picture, okay. And due to that reason this point is written, okay. So suppose I have graph, so I can able to see that two graph are closer or not, but at that time we are not going to involve the numbers, okay. So topological space is more general kind of space, okay. So in this lecture I am not going to talk much about the topological space, just I am going to talk about open, close, and those kind of concept which is coming from the topological space, okay. So a topological space is set of point along with the set of neighborhood, okay. So whenever we are defining the topological space, at that time we are defining everything in terms of the point and their neighborhood, okay. And after that obviously some axioms is there. So in this way we are actually quantifying the topological space, Okay, and in mathematics, topology is concerned with the property of geometrical objects. If you see carefully, then somehow topology is connected to the continuity. Okay, so they are telling that if you apply the continuous deformation such as stretching, twisting, crumbling, and bending, then property of object will not change. Okay, but if you do this kind of operation, then their property will change. Okay, so it might possible that two things will look very different, but that is topologically similar. Okay, so that is the basic idea. So again, with help of norm, I can able to define the closeness of the graph. Okay, and geometrical object or graph you can tell. Okay, now let us come to the open set. Okay, so here we are going to take the help of the topology somehow. So now here I have give the definition of interior. Okay, so what is meaning of definition of interior? So let P is the subset of norm space X. So whenever we are talking about norm space, means X, I have vector space as a X, and after that I have some kind of operator. This operator is called norm. If you are going to apply this operator on this vector space element of this vector space, then you are going to get some kind of positive real number. And due to that reason, whenever we are talking about the norm space of X, basically we are talking about some kind of ordered pair where I have vectors, and I have actually one associated norm with that particular vector. Okay, now what we are telling that PB is subset of a norm space X. It means that now P I have selected from this X, again distance is defined. So in place of X, now I can put P. Again that will map to some positive number R plus. Okay, so the point P, now what I am telling that P is subset of X. Now if P is subset of X, then they have several points. Okay, point may be in form of column vectors, again may in form of functions or matrices, that doesn't matter. Okay, because point is nothing but element. Okay, so P belongs to P is said to be interior point of P if there exists a epsilon such that X satisfies this kind of relationship for all member of P. Okay, so you can take any member of P, and if that will satisfy this kind of property, so collection of all interior point of P is called interior of P, and that is denoted by this. Okay, so now here you can see that by mapping this I can able to get some kind of number, because if I apply this kind of real valued function in higher dimensional space, then I am going to get some kind of real number. Okay, so finally if I will get real number, then I can tell that now I am in on real line, so I can tell that this point is going to lie in which side of the number. Okay, and due to that reason epsilon is nothing but some kind of a scalar. Okay, so this notion here I can also able to now define or generalize something, that is notion of ball. Okay, so somehow norm in higher dimensional space also gives the notion of the ball. Okay, now here please be careful, ball may be some kind of line, maybe some kind of point, maybe some kind of means a sphere, maybe some kind of circle. Okay, so that depending on the shape. So ball is very general, a general notion. Okay, so we have defined ball, and here x is the center and epsilon is the radius. So we are going to define the ball or a sphere with the help of the norm. Okay, so suppose if you are in one dimensional space, then at that time this is nothing but just that is given by the some kind of absolute value. Okay, because in one dimensional space norm and absolute value is exactly the same. So if you plot this, then that is nothing but some kind of line. Due to that reason I am telling that this ball may be a line. Okay, and suppose these points are the same, then that might be a point. Okay, if you are in two dimensional space, then x1 minus y1 square and x2 minus y2 square less than epsilon, something like this that comes into picture. Okay, so in this way I have some kind of circle. Okay, and if we are in three-dimensional space, then I have a sphere or some higher dimensional. If we are in higher dimensional, similarly I have some kind of ball in that space, that particular space, and due to that reason I have given generalized name. Okay, so sometimes people are writing ball, sometimes people are writing the sphere. Okay, now according to above definition, a point x is the interior point of P if a sphere means I am talking about the ball centered at x and contain P. Okay, so interior means what basically we are going to do, that if I have to check that some point is interior of that, I will take some point and I am going to construct some kind of a sphere, and I have to make sure that that is going to lie inside this P, then we are telling that that is the interior point. Okay, so a set P is said to be open if P is equal to interior of P, that is denoted by, so interior means collection of all point I am telling. Okay, so entire space is a open set. Okay, if we are just talking about the real number. Okay, so real line is nothing but a open set, and unit sphere consisting of all vector in this form is also a open set. Okay, so now if you are in unit sphere, you can take any point and you can construct the ball, and after that this ball is inside this only. Okay, because equality is we are not able to keep here, and due to that reason this is open set. Now another notion that is again coming from the topology, that is the closure. Okay, so closure, a point x that is the that belongs to vector space X is said to be closure point of P if there exists epsilon greater than 0 and there is a point P satisfying this kind of relation. So collection of all point of P is called the closure point of this. So these are the just definition, because several places we are going to use this kind of definition. So just please try to understand that whenever I am talking about closure, meaning is that I am going to talk about the point X, and whenever I am telling that closure point set P, then that is the meaning, and due to that reason I have written this kind of definition. Okay, and again now whenever we are talking about closed set, at that time we are going to talk about the closure. Okay, whenever I am going to talk about the open set, then we are going to talk about the interior. Okay, and here whenever we are going to talk about the closed set, I am going to talk about the closure point, all closure point of P. Okay, and definition is like this. Okay, so now from topology two things become clear, that interior, closure, open and close. Okay, so using based on norm we are able to define these kind of topological notion. Okay, so these notion are not very much relevant for us, but at least we are able to understand that I can able to to know that something is open or something is closed or not. Okay, now let us come to the definition of limit. Okay, so in order to talk about the definition of limit, I have to talk the definition of convergence. Okay, so what basically we are telling, I have some kind of sequence. Okay, so here sequence xi may be the sequence of column vectors, sequence of functions and sequence of matrices. Okay, so sequence basically we are representing like this, I, and like this, I equal to 1 to infinity. Okay, so every and I equal to 1 to infinity means 1 2 3 4 5 means only positive numbers we are taking whenever we are defining this sequence. Okay, so now what we are telling, that this sequence, and suppose if I have non-linear space, and non-linear space, then I have vector space with norm, is said to be convergence at point x equal to x0 that belongs to x. Okay, so this sequence is going to converge to x0 if for every epsilon there exists an integer, and integer, now you can see that this integer is function of epsilon such that this relation will satisfy. Okay, so whenever some sequence is given to you and you have to prove that that is going to that has limit or going to converge to some point x0, then this relation should be satisfied. Okay, so in this way I can able to talk that x0 is limit in this space for this sequence or not. Okay, so if some sequence is given to us and now that is going to converge to limit point or not, that I can able to check using the notion of epsilon. Okay, so for every epsilon there exists, if there exists a number, then I can able to talk that that is going to converge. In this way I can tell that x0 is the limiting point, okay, or limit. So using the notion of convergence, I can able to define the limit point x0. Okay, anyone has confusion? It means that in order to talk about convergence, first I have to understand that there exists a limit. Then only I can able to talk about the convergence. Okay. So if I don't know the limit, then I cannot able to apply this kind of definition. Okay, so let us try to see the remedy of this, how to deal if I don't know the limit. Okay, then how to deal with that particular situation. Okay, if I know the limit, then I can tell epsilon greater than 0. I will solve this. So I can open this norm. So I can open this norm in various way. Okay, because if you are in finite dimensional space, then all norm are equal. Okay, so in that way you can able to define n. After what bigger n, this will converge. I will send you some tutorial because I have prepared some kind of tutorial based on the notion of convergence. Okay, how to calculate epsilon and epsilon ball and corresponding n for that. Okay, that is very easy, not difficult task. Okay, now what happens that we are telling that I have some kind of norm linear space and I have some kind of sequence in this particular norm linear space, and sequence is actually 1 to infinity. And now I am going to talk about the convergence of this sequence at x0, and x0 is actually belongs to this x. Okay, so whenever we are going to talk about the convergence, okay, so basically we are defining in terms of epsilon. Epsilon is very any number if you take, any large number if you take, then corresponding n comes into picture. Even if a smaller number epsilon you can take, then some n comes into picture. So you can able to decrease this number to 0 also. Okay, so if you are able to decrease this number up to 0, then it means that x minus xn is converges to 0. Okay, and due to that reason means either you can write this definition, or you can write this definition, that a norm linear space, an infinite sequence xn is said to be converged to vector x if sequence itna of real number converge to 0. Means x minus xn with norm, you can take any norm of real number converges to 0, and then I can able to write like this, xn tending towards x. Okay, so either you can write this definition and this definition, both are equivalent. Okay, so for computer, suppose that if you want to test using machine that something is converging or not, if you substitute 0, then calculation time is very large, and due to that reason always people are substituting some kind of epsilon value, a small epsilon value, and they are checking that for every epsilon there exists n or not. If that is the case, then they will give guarantee that even if epsilon is very small, then I can able to define the n. Okay, now here means these two definitions are the same. Why you are able to see that xn, if xn converges to x, then I can able to write norm of this will converge to norm of this. Okay, and I can able to write this, so due to that reason this. So in this way we are able to see that both definition are the equivalent. Okay, and if a sequence is converged, then its limit is unique. Okay, so uniqueness, whenever you have to prove uniqueness, then you can assume that that is converged to two different points, x and y. Okay, and finally you can show that x and y are both are the same point. So same kind of things I have done here. I have some kind of infinite sequence xi. Okay, and I am assuming that xn is going to converge to x, and xn same sequence is going to converge to another point y. Okay, now what we are going to see, we are going to check the distance between x and y. So if you check the distance between x and y, since xn is going to converge to x, it means that x minus x1 equal to 0. Y is xn is going to converge to y, so this is 0. Due to that reason, this x minus y is tending towards 0, so it means that x equal to y. It means that limiting point when some sequence is going to converge in non-linear space, that is unique. Okay, now same kind of things in another way, we have already seen that I can also talk in terms of the sphere. Okay, so epsilon delta concept, whenever we are epsilon and n concept. Okay, so what basically we are telling, that for every epsilon greater than 0, there exists n, and n is function of the epsilon. I have to just check this relation, that xi minus x0 norm of this, that is less than epsilon. Okay, and this is true for all I. Okay, so if this will true I for all I greater than equal to n. Okay, so I have to check this kind of things. Okay, so somehow you can see that using this notion, this is nothing but notion of ball or a sphere. Okay, whatever. So now what we are telling, that if some sequence is converging, then it is possible to show that as I is greater than some number n, then all value of sequence, okay, all numbers that is going to generate, that is going to lie inside this sphere only. Okay, same kind of things I have written here. Okay, and a function f is closed if and only if every convergent sequence with element in f has its limit in f. Okay, so we have already defined closed using the help of closure. Okay, using the help of topology, we have defined what is meaning of the closure. Okay, now this statement is relating the notion of convergence with the closeness. Okay, so a set f is closed if and only if every convergent sequence with element in f has a limit in f. Okay, so what does it mean? So suppose I have some kind of convergent sequence. Okay, and then I can tell that whatever set f, that is closed, and if that is closed, then I have convergent sequence with limit. Okay, so both sides will true. That is the meaning of this proposition, and this is the proof. Okay, so proof is not so important for us. Okay, so just sake of the completeness I have written here. So basically the limit of sequence f is obviously a closure point of f, and because whenever we are talking about the convergence sequence, at that time we are giving definition like this. Okay, and if you see carefully the definition of closure, again come to the definition of closure, so definition is exactly the same. Okay, so for p belongs to p, this relation should satisfy. Okay, so you can interpret x as a limiting point x0 and p as a all point of sequence. It is possible to show that this relation will always satisfy, and due to that reason we are telling that if f is closed, then every convergent sequence with element has a limit in f. Okay, so that is obvious from the definition. So far what we have seen, that I have some kind of a space. Okay, and now I know that how to define the notion of distance in the space. Okay, what another thing we have noted, now I have infinite many way to define the notion of closeness or distance in some space. Okay, so you can take any norm, every norm is going to introduce some kind of distance in some kind of vector space. Okay, and that is called non-linear space. Okay, and after that what we found, that I can also able to talk about the convergence if I have some kind of sequence. Okay, and if that sequence has limit, then it is possible to show that if I construct some kind of ball around that limit, so suppose that I have a space x and x0 is limiting point, So I can able to construct some kind of ball of epsilon, length epsilon, such that this sequence from from any point it is possible to show that will satisfy this kind of relationship for epsilon ball I have constructed. Then I have to wait for natural number n, and so there exists a natural number n, and that is epsilon. So I have to wait for this natural number n. Then it is possible to show that all element of this sequence. Okay. So xi is the sequence and x0 is the limit. Then that is satisfy this kind of relationship. It means that after this number, okay, what happens, that sequence, all value of sequence is only going to lie inside this region. That is the meaning. Okay, but in order to talk about the convergence, I have to know the limit. Okay, now people are trying to avoid this kind of information, because it might possible that I am in some space and some arbitrary sequence is evolving, because most of time if you see the real situation, I do not know exactly the sequence. Okay, and due to that reason I cannot tell that what is the exact limiting point. Okay, particularly whenever we are going to deal with the dynamical system. Okay, so assuming that there exists a limit point, and I know the limit point is very restrictive assumption. Okay, so it might possible another way, we can just assume that there exists a limiting point, but I don't know the limiting point. Okay, so another notion that is called the Cauchy sequence. So what Cauchy sequence is telling, that if xn is some sequence, so whenever I am talking about sequence, so also just for simplicity I have actually remove I equal to 1 to infinity, in a non-linear space is said to be Cauchy sequence. Okay, so just now we have seen what is meaning of convergence sequence. So if I have some kind of convergence sequence, it means that if I have limiting point, then for there exists some kind of number, natural number n, such that after this number this relation will satisfy, means all value is going to lie inside this ball. Okay, now I am going to define the another notion that is called Cauchy sequence, and Cauchy sequence is telling now the distance between two 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 sequence. What they are telling, that here in this convergence sequence we are always evaluating distance from the limiting point. Okay, suppose this distance is not known to me, then I can able to define the distance between any two consecutive sequences, and same kind of things I have done here. So a sequence xn in a non-linear space is said to be Cauchy sequence if xn minus xm tending towards 0 as n and m tending towards infinity. Okay, so now here you can see that I am not going to involve any limiting point. I am telling that I have taken any two arbitrary sequence, okay, n and m, and n and m I am going to increase up to infinity, and if that is Cauchy sequence, it is possible to show that there again exists some kind of n, such that xn minus xm is less than epsilon. Okay, in the previous case, whenever we are talking about convergence sequence, then this xm is x0 and xn I am only varying. Here I am varying everything, n and m both. Okay, and then we are telling that if this relation will satisfy, then I am going to give another name, that is Cauchy sequence. So you can see that in order to talk about Cauchy sequence, there is no need to know the limit. Okay, so even if limiting point is not known to me, I can select two sequence xn and xm, and then we will see the distance between that. And if this relation will satisfy, it means that for every epsilon greater than 0 there exists a n, and again this is function of epsilon. Okay, and now what I have to do, I have to see distance between these two sequence, that should be epsilon, and for all n and m, and that should be greater than n, and n is function of epsilon. If we are able to do that, then we are going to define that sequence as a Cauchy sequence. And it is possible to show now if some sequence is convergent sequence. Okay, so convergent sequence means this kind of definition will satisfy. Okay, then that is also Cauchy sequence. Okay, so it is not very difficult to prove. What you can do now, you can see that if some sequence is the convergent sequence, it means that that is going to converge to some limit. So I have to show that xn minus xm is less than epsilon in case of the convergent sequence. Okay, so and in convergent sequence we know that if this relation will satisfy, so indirectly meaning of this is that xn is tending to x0. So same information I have used here, xn minus xm, and I am going to add x and subtract x, and after that I am going to use the norm inequality. Okay, we have already discussed about this inequality. Okay, so now xn is tending towards x, and xm means if I have convergent sequence, we have already seen that limit is always unique, and due to that reason xn and xm that is going to converge to same point, and that is going to converge to 0. So either you can write in terms of epsilon and 0. I have told you that both are exactly the same notion. Epsilon and I can decrease to 0. Okay, so it means that any convergent sequence will also Cauchy sequence. Okay, so if you try to see the difference between convergent sequence and Cauchy sequence, the difference is now clear. If I know the limiting point, so I am going to calculate the distance from the limiting point. If I don't know the limiting point, then I am going to see the distance between any two sequence. If that is decreasing, okay, then I can always be able to find some natural number n such that distance between two sequence is going to fall inside this ball. Okay, now try to see the reverse. Okay, so what we have seen just now, if I have convergent sequence, then that is also Cauchy sequence. So now question is that all Cauchy sequence is also convergent. So answer is not. Okay, always that is not possible. Sometime it might possible in best case that Cauchy sequence is also convergent. Okay, so convergent is always Cauchy, but Cauchy may or may not be convergent. So norm space in which every Cauchy sequence is convergent sequence are particularly interest in analysis. Okay, so but what is beauty of Cauchy sequence? That Cauchy sequence, at least I can tell that even if there do not exist the limit, but they are converging. Okay, so suppose that I have some kind of Cauchy sequence and that is also convergent. Okay, so Cauchy sequence is not always convergent, but it might possible. I have some case where Cauchy sequence is also convergent. So I am going to just identify those kind of space. Okay, and why that space is very important because now we don't know the limit, but at least I know that if I take any two sequence, that is going to converge. Okay, and that space is called complete space. So a space in which every Cauchy sequence has a limit and therefore convergence is said to be complete. Okay, so complete space is very much important for us. It means that if I just check any two sequence, then they are converging towards each other. Okay, and they have also limits. So finally, even if I don't know limit, they are going to converge to that limit. Okay, and due to that reason, some name of some new space that comes into picture, that is called Banach space. So a non-linear space X is complete if every Cauchy sequence X has a limit in X. Okay, so what we have seen that Cauchy sequence generally do not a convergent sequence, but if there exist those kind of Cauchy sequence which is also convergent or that has a limit, then that space is complete space, and that complete non-linear space has very special name that is called Banach space. Okay, and now when I have started this class, I have told you that whenever we are solving the optimization problem, at that time I am assuming some kind of a space. Okay, and it is possible to show that a space is Banach space. Why? Suppose that I have some kind of minima here, okay, or some kind of maxima here. So this is just two-dimensional space I have taken, but it might possible I am in higher dimensional space. Okay, I don't know what kind of geometrical structure I have. Okay, so at that time, in order to identify this minima, I have to always, if I am starting from here, so I have to check the distance, and finally I have to show that distance between these two are decreasing, and finally I can able to claim this minima or maxima. Okay, so if that is not complete space, it is possible to show that I cannot able to come here or here. Okay, and due to that reason, whenever we are talking about the optimization problem, at that time we are assuming that our underlying space is Banach space. So due to same thing I have basically written using this sentence: when seeking an optimal vector maximizing the given objective, we often construct a sequence of vector. Okay, so whenever we are solving optimization problem, always we have some kind of performance measure. Okay, and we have to minimize or maximize that performance measure. Okay, and we have certain kind of criteria. Okay, so same kind of things are telling that each number of which superior to the preceding number, the desired optimal vector is then the limit of the sequence. Okay, so either we are talking about maxima or minima, that should be limit of the same. And due to that reason, if I assume that underlying space is Banach space, so I can start with any two sequence, and finally I can converge to the desired point. Okay, so now I hope that you are able to understand the relation between these two. So let us try to see some kind of actually sequence which is not not form a Banach space or incomplete norm space. Incomplete norm space means all Cauchy sequence is also not convergent. Okay, complete means all Cauchy sequence is also convergent. It means that without caring about limit, I can able to proceed with two sequence, and I am going to land to the limit. Okay, so what we are going to do, we are going to again take the space of continuous function. Okay, so whenever we are talking about a space of continuous function, and if I define pointwise addition and scalar multiplication, pointwise scalar multiplication, then that will form the norm linear space. We have already seen. Okay, and norm we are going to define like LP norm like this, that we have something like 0 to 1, because I have to give the limit, and after that here xi x, and after that x is some kind of vector, and after that we are defining like this x power p and 1 by p, something like this, and in this way basically we are going to define. Okay, now here please try to see that, and here we have basically dx or something you can write. Okay, now or something dt means whatever underlying function, because for all time we are integrating 0 to t. Okay, now what we have done, we have defined that this norm like this. Okay, so here absolute value I have keep inside this. Okay, so again all property of norm will satisfy, so it is possible to show that this is norm linear space. Okay, so now we are going to show that x is incomplete. So in order to show incomplete, what you can do, you can generate any one sequence, because whenever some space is complete, then every Cauchy sequence is convergent sequence. Okay, so now just you can generate one counter example, and people has generated this kind of counter example. Okay, they have defined this sequence. They are telling that if t that lie on this region, then that is 0, when that will satisfy this, then this, and when t is greater than equal to 1, then this is 1. Okay, it is possible to show that if you take any two sequence, distance between any two sequence, that is going to converge to the 0. Okay, but individually if you see that is not going to converge anywhere. Okay, so limit will not exist. Okay, but distance between any two sequence if you take, then that is going to converge to 0. Okay, so this space is called the incomplete space. It means that if you define norm like this, if you have continuous function, okay, then you are in dangerous situation. Okay, so due to that reason, means you are able to see that whenever we are solving the optimization problem, at that time we are not defining norm like this. Okay, Now let us try to see the another example. Another example is like this. We have constructed this kind of vector and we are actually defining norm like this. Again, norm will satisfy all the property, and it is possible to show again that if you take two sequence, okay, so maximum value if any sequence, that is unity, okay, 1 by 2, whatever sequence you can tell, and maximum we are defining the norm like this, so that is unity, so any two sequence is going to converge to 0, okay, but it is possible to show that even if you can take any finite sequence, then limit will not exist, okay, so again this space is incomplete space, okay. So now it is time to conclude the today's lecture. So what we have seen in today's lecture, that I have some kind of a space, okay, and a space will satisfy the property of vector space, okay. Using the notion of norm, I can able to define the distance, which will satisfy all three property, okay. Now with that notion of norm, I can able to define the convergence, okay. So if I know the limit, then it is very easy to define the convergence. But several places, suppose that if I have to solve optimization problem, I don't know the limit, okay, and due to that reason we are relying on two sequences, okay, two converging sequences. If our space is complete, it is possible to show that every Cauchy sequence means those sequence which are converging towards each other also has a limit, okay, so that is convergent sequence, okay, so that space is beneficial for us, okay. So whenever we are solving generalized problems, sometimes people are not caring about the space, and in this way what happens, that they are not able to optimize something, so they are thinking that something is optimized, but a space is not complete, then we are not able to actually get that optimal point, okay. And due to that reason, you have to know that whenever you are solving some problem, what kind of a space is involved, what kind of norm is involved, okay, because every norm is going to give you new notion of the distance in that space, okay. So with this remark, now class is in from my side. If you have any question, then please let me know.
Sir, what is the difference between a non-linear space and an Euclidean space? Both have the
No,
notion of length.
no. Actually, whenever we are talking about Euclidean space, at that time, whatever whatever vector I am considering in Euclidean space, if you see carefully, then we are talking about vector in form of column, okay, and column, each entry of column is some kind of real number. And how basically we are defining the distance? In order to define the distance, we are taking the help of dot product, okay. Dot product means, suppose you have point x and y, then we are defining x1 minus y1 square, x2 minus y2 square. We are not actually generalizing the notion of distance, we are just limit ourselves in that kind of distance only, okay. So I have element in form of the real number, and distance is defined with the help of dot product, or you can tell that standard inner product, because dot product and standard inner product is exactly the same. Now whenever we are talking about norm linear space, at that time, now I have generalization. So element might be in form of column vector, might be in form of functions, might be in form of matrices, okay. So here flexibility comes into picture. After that, distance also don't have any restriction, you can define the distance in many various way, okay. So if you check the previous class, then I have taken, suppose I have some kind of element in functional space, then how to define the distance? When that is in form of column space, then how to define the distance, okay. So in Euclidean space, I have vectors in form of column vector, and L2 norm we are telling. L2 norm means x1 minus y1 square, x2 minus y2 square, xn minus yn square root of that, whatever during school time, whatever we have done, okay. So that is the difference between the Euclidean space and nonlinear space. So
Okay, sir.
okay, so now things become more general, and I have told you that why different notion of distance is required. Suppose if you take Ola taxi, okay, and whatever distance, notion of distance in Euclidean space, that is always telling that x1 minus y1 x2 minus y2 square root of that is shortest distance. Okay, but sometimes shortest distance is not feasible. Okay, there is no road. Suppose you are at point A and B, so and suppose there is no direct road from A to B, so you have to take the alternate distance. Okay, so you need some kind of measure of distance. Okay, so using L2 norm, you are not able to calculate the distance, so you have to take the help of L1 norm, L infinity norm to solve the same problem. Okay, and due to that reason, in practical reality, several problems that is not going to solve using Euclidean space or notion of Euclidean space. Suppose if you have function, okay, whenever you are going to solve the LQR problem, at that time you have to minimize the functional, and that function comes into picture. I don't know how to calculate distance between two functions, so I cannot able to solve, and due to that reason, more general space, non-linear space is required. Is it
Okay,
is
sir.
it clear to you now?
Yes, sir.
So believe on me, these kind of notion required some kind of maturity. Okay, so what is my request to each and every students? Whenever you are finding some kind of a space, try to make some kind of cheat kind of things, and you try to write. Suppose I have Euclidean space, then what is meaning? Whenever I have vector space, what is the meaning? Whenever I have non-linear space, what is the meaning? Whenever I have Banach space, what is the meaning? Whenever I have Hilbert space, what is the meaning? Whenever I have inner product space, what is the meaning? And in this way, things become more clear to you by doing the comparative study. Okay, obviously in the whenever I am going to end this part, then I think that I will make one complete slide where all kind of spaces comes into picture, and then I will tell you the story. Okay, so thank you very much. Now if you don't have any question. Okay, tomorrow I am not going to take class because I have some important means meeting. Okay, so I will take that class, might be on Saturday or Sunday or some sometime I am going to shift that class. Okay, so thank you very much.